Hey everyone, and welcome. Today, we are going to get our hands dirty with a concept that honestly keeps the whole internet from falling over. We're going to design a rate limiter. You've definitely seen this before, right? You're hammering that refresh button, trying to snag concert tickets or something, and bam, you get hit with error 429, too many requests. It's frustrating for sure, but that message is actually a good thing. It's a sign that a really important system is working exactly like it's supposed to.
Yep, that error, that's a rate limiter doing its job. It's basically the internet's bouncer. And in this explainer, we're not just going to talk about what it is. No. We're going to architect one together from scratch as a fun little design challenge.
So here's our game plan. We'll break this down into 5 key steps. First, what even is a rate limiter? Second, where does it live in our system? Third, and this is the fun part, we'll pick the right algorithm. Then we'll sketch out the architecture and finally add those all-important finishing touches. So let's start with the absolute basics. What is this thing, really, and why do we even need it? What problem is it solving? At its core, a rate limiter is pretty much what it sounds like. It's a system whose entire job is to control the rate of requests. It puts a cap on how many times a user, or an IP address, or some other service can hit you up in a certain amount of time. Like 100 requests per minute, max. And why is this so critical? Well, it boils down to 3 huge reasons. First step, security. This is your frontline defense against things like denial of service attacks, where someone tries to flood your servers and take them down. Second, it saves money. It controls traffic so you don't get surprise bills from other services you rely on. And third, plain and simple, it prevents your own servers from getting overloaded, which keeps things running smoothly for all your legitimate users. Okay, so we're sold. We definitely need one. The next logical question is, where the heck do we put it? This is a really big design decision. Now, you might think, hey, why not just put it on the client side, in the browser or the app? Well, let me tell you, that is a terrible idea. It's a total non-starter because anyone with a little bit of know-how can just bypass it. Nope. The only place this can reliably live is on the server side, where you have complete, total control. And to be more specific, the modern way to do this is to implement it as its own middleware layer. Picture it like a dedicated security checkpoint that all traffic has to pass through before it even gets a chance to talk to your main application. This is often handled by something called an API gateway, which is perfect for this kind of thing. Now we're at the heart of the design. This is where it gets really interesting. How does the rate limiter actually decide who gets in and who gets blocked? It all comes down to the algorithm. A really popular choice, we're talking Amazon, Stripe, companies like that, is the token bucket algorithm. Just imagine a literal bucket. It's constantly getting refilled with tokens at a steady pace. Now, every time a request comes in, it has to grab a token from the bucket. If the bucket's empty, sorry, you're out of luck. The request gets blocked. What's so cool about this is it naturally handles short bursts of traffic because you can use up any tokens that have been saved up. But hold on, couldn't we just do something way simpler? Like just count the requests in a given minute? That's called the fixed window counter algorithm. It's super intuitive, which is nice, but it has a massive loophole. Okay, look at this timeline, because this is where it all falls apart. Let's say our limit is 5 requests a minute. A user sends 5 requests in the last 30 seconds of a minute. Cool, they get through. Then, at the top of the next minute, the counter resets to 0, and they immediately send 5 more requests in the first 30 seconds. They also get through. See what happened? They just sent 10 requests in a 60-second span. Double our limit. The system got totally played. So how do we fix that glaring hole? The answer is to use a sliding window, one that always looks at the last 60 seconds from the exact moment a request arrives. And there are basically 2 main ways to pull this off. On one hand, you've got the sliding video log. It's perfectly accurate because it literally logs the timestamp of every single request. But as you can probably guess, it can eat up a ton of memory. On the other hand, you have the sliding window counter. It's a clever hybrid that approximates the count. It's way more memory efficient, but it's not 100% accurate. And right there, that's a classic engineering trade-off. All right, we've got our logic picked out. Time to zoom out and look at the big picture. Let's actually put these pieces together and see what our high-level system looks like. So we have all this data to track for every user, counters, tokens, timestamps, you name it. Where are we going to keep it all? A traditional database is just way too slow for this. The rate limiter itself would become a massive bottleneck. The answer is a high-speed in-memory cache, and the absolute king of this space is Redis. It is incredibly fast, and it has commands built right in, like incur to increase a counter and expire to automatically delete stuff after a set time. It's almost like it was purpose-built for this exact job. And here's the entire flow. A request comes in and hits our middleware. The middleware makes a lightning-fast check to Redis to see the current count. If the count is under the limit, it tells Redis to increase the count by 1 and lets the request go through to the main API. If the limit's already been reached, boom, it immediately sends back that 429 error. Simple, elegant, and crazy effective. We're in the home stretch. The main engine is built. But now it's time for the professional touches, the stuff that makes it robust and, actually user-friendly for the developers who have to interact with it. See, a really great rate limiter doesn't just put up a wall. It's a helpful guide. And we can do that by using HTTP response headers. With every single response, we can tell the client, hey, here's your total limit. Here's how many requests you have left. And, this is the important one, if they get blocked, here's exactly how many seconds you need to wait before you try again. This is an absolute lifesaver for developers. And hey, remember that trade-off we talked about between the perfectly accurate algorithm and the more efficient one? Well, get this. Cloudflare, one of the biggest networks on the planet, ran an experiment on 400 million requests. They found that the less accurate memory-saving algorithm was wrong only 0.003% of the time. For most systems, that is an incredible trade-off you would take all day long. So finally, what's the takeaway for you as a developer using these APIs? It means you have to be a good API citizen. Cache data on your end so you don't have to make so many calls. Actually read the docs and understand the limits. And most importantly, write your code to handle that 429 error gracefully. When it tells you to wait, wait. So I'll leave you with this final thought. Your app just hit the big time. It's going viral. Traffic is exploding. What's going to save your servers? The memory hogging algorithm that's perfect but might crash, or the super efficient approximation that gets it right 99.997% of the time? That choice? Well, that's system design in a nutshell. Thanks for diving in with me on this one.